All right, for lecture A, I modified some code here to make things look nicer. I added in some different coding options that you see here, got rid of the frame, changed the plot range a bit to make the graph look nicer for the velocity as a function of time. So if I was going to label the axis here, which you really should do, I label the horizontal axis t and the vertical axis v. We're looking at the slope field for this differential equation here. The right-hand side of the differential equation, I call f of v in this case, only depends on v. There's no t's on the right-hand side. You make the slope field in the TV plane here, you're going to get constant slopes along horizontal lines because the right-hand side does not depend on t. And that's what we see in the picture. And the solution curves do have a slope everywhere given by the right-hand side of the differential equation. So you get a picture like this. Notice again that along any horizontal line where v is constant, v is the vertical axis here, your line segments have the same slope. They don't depend on t at all. You get a solution when the initial velocity is 0 that goes like this. That means you're letting the object go from rest. It's speeding up because the velocity, moving downward because the velocity is becoming more and more negative. And it does keep speeding up. It does keep accelerating because this function goes down. However, the absolute value of that acceleration gets closer and closer to 0 because the slope of this gets closer and closer to 0. It has some sort of horizontal asymptote. That horizontal asymptote would be what's called the terminal downward velocity. Maybe I should say it as the terminal upward velocity because it's a negative velocity here. Around negative 100, it seems, for an object in the Earth's gravitational field where g is 9.8, and such that the constant proportionality for the air resistance is 0.1, and mass is 1. If I change those numbers, change k and m first, change k, change m, what happens? The terminal velocity changes. I increased both k and m, and now the terminal velocity is more like close to negative 60 here, it seems. If I change g, I change the terminal velocity. If I increase g, that's a stronger gravitational field. Terminal velocity should become more negative, should go down. Yep, it went down. If I decrease g, like on the moon or Mars, it's a smaller g, then the terminal velocity is not as negative. And yes, again, if you start off with a positive velocity, if v0 is positive to start with, then yes, the object does move upward for a while before it starts coming back down. Could I take this information and use it to graph the height as a function of time as well? Sure. All you have to do is integrate the velocity. That's essentially a differential equation as well. dv dt equals this, but that's a pure antiderivative problem. You can just straight integrate that function to get a formula for the height. I can just copy and paste this whole thing, put it next to an integral, integrate with respect to t. Keep in mind that there would also be an integration constant, a plus c, and that c would be related to the initial height. And then you could graph that. I won't take the time to graph it in Mathematica, but if you did, you could get a graph that looks like this, or like this, depending on what the initial velocity is. This would have a positive initial velocity, where the height is a function of time. This one has a negative initial velocity. A zero initial velocity would look about like this. Kind of look like parabola, so you might think it would be like the free fall with no air resistance, but actually these are not parabolas. I believe if you graph them, including for when y goes negative, they have vertical asymptotes, I believe. Actually, I'm not sure about that. Yeah, probably not actually, looking at the formulas, but they're not parabolas, okay? And the air resistance is what's causing them to not be parabolas. All right, New model for lecture B is going to be a mass on a spring or harmonic oscillator model, leading us also to systems of differential equations and the idea of a phased plane, which we will only be able to touch on today. So we have a drawing of a mass on a spring. We have a wall over here, immovable wall. We have ice down here. We don't want any friction here initially. Mass on a spring. This spring, we're going to assume has no internal friction. Ha ha ha. That is obviously not true. LOL. But for the sake of keeping things simple, we assume it's such small friction that it's negligible, and we see if we can solve it in the simple case before we try a harder case. That's a common theme in applied math, is you try simple things first, even if they're not accurate, to see if you can solve them in the simple case. Once you solve the simple case, you see how well it reflects reality. If it's pretty good, then maybe you stick with it. If it's not so good, then you try a more complicated model. So we want to keep things simple as possible. Okay, no air resistance either. I guess we're in a vacuum. Okay, getting rid of all friction as much as possible. Let me go ahead and call the dependent variable x this time instead of y. That's okay to do since it's horizontal back and forth. We're going to have back and forth motion. X equals 0 is, say, where the mass is at rest. The center of mass is at x equals 0. When we pull the mass to the right, then the position is positive. If we squish the mass toward the wall, the position becomes negative. In either case, pulling or pushing, we can let it go from rest and it oscillates back and forth. And if there really is no friction, it'll oscillate back and forth forever, we would think, at least. We can also give it an initial velocity. We can hit it with a hammer. If we hit it with a hammer like that, then we have a negative initial velocity. If we hit it with a hammer like that, then we have a positive initial velocity. Okay? Lots of different things we can do with this setup to see what happens with motion. We are after, the goal here is to find x as a function of time. Now you can certainly do this kind of stuff without differential equations. You can guess that x is going to be a trig function. And that guess is pretty accurate. But we also want to see how the physics leads to that guess. Partially because it'll confirm the physics is being consistent with that guess, which is not a small thing. It's a good thing. And secondly, it will help us, by doing the physical approach, it will help us apply it to more difficult situations like where we do have friction. Or where we've got maybe some sort of external forcing, like we hit it with a hammer every second. That would be like an external force, and we might want to have to deal with that kind of situation too. So again, with the physics, Newton's second law, N2, is going to be my abbreviation for Newton's second law because we're going to use it a lot here. F equals ma. Now A is dx dt, dv dt, where v is the velocity, the rightward velocity, or the second derivative of x with respect to time. X is not a height, it's a horizontal position here. But once again, what's the force? The force is due to Hooke's law. We talked about this before. Remember when we were talking about work done by a force, we were talking about this exact same situation. The force is a negative constant times x. When you pull the mass away from its rest position in the positive direction, the force is in the negative direction. This needs to be negative quantity when x itself is positive. When you squish the mass, squish the spring toward the wall, x becomes negative. The force points in the positive direction. You have a negative times a negative, giving you a positive force in that situation. This is a differential equation. It's a second order equation because it involves a second derivative. And a standard way to write it is to get well, okay, I could write it like this. I could also divide everything by m and write it like this. And sometimes people also add k over mx to both sides and leave 0 on one side to write it like this. All three of these ways of writing it are fine. Okay? Any one of those is a fine way to write it. I guess I could add kx to both sides of this one as well to get a fourth way to write it. What are solutions of this? Again, you might, even without thinking about differential equations, you might guess cosines and sines. However, one benefit right away of having the differential equation is because of the fact that you have a k over m there, that can help you figure out what the period of the oscillation should be, the frequency. Should help you be able to figure out the multiplier of the t inside the cosine and the sine. Here's what I mean. We could guess an answer here that the general solution, x as a function of t, is some constant a times cosine of something plus another constant b times sine of something. The something should involve a t in both cases, but what should go in front of the t? It should be related to k and m if you wanted to solve this differential equation. If you think about it carefully, and think about differentiating this twice with the chain rule, the square root of k over m is what you want to multiply t by. Check it in your mind. Differentiate cosine of t, you get negative sine of t, but you got cosine of this times t, you're going to get an extra factor of that square root in front. When you differentiate again, when you find the second derivative, you're going to get another factor of the square root of k over m. So you get square root of k over m squared, and the square root goes away, leaving you with just k over m. And with a negative sign in there, since the derivative of cosine is negative sine, and the derivative of negative sine is negative cosine. That's where that negative matches up, and the k over m is right there. You can check this works. Maybe I should go ahead and write it down. I'll just go ahead and write down the second derivative right away. The second derivative you're going to get here is going to be negative a times k over m times cosine of square root of k over m t, and minus b sine of, minus b times k over m sine of square root of k over m. I used the chain rule in my mind there a couple times, getting a square root of k over m in front each time. And this is negative k over m times the original function, times x. It solves this differential equation. It is a solution. This guess does work, as long as the coefficient of t is square root of k over m. Is that an accurate model? You'd have to test it with experiments. So you'd have a mass on a spring. The first thing to test, probably as far as the accuracy goes, is the period or the frequency correct? The period, according to this model, should be predicted to be 2 pi over the coefficient of t, square root of k over m, which can be simplified to 2 pi times the square root of m over k. So you watch that mass on a spring going back and forth. You get a stopwatch out. Your phone, stop phone. And you see how long it takes to go through one oscillation. Or maybe how long it takes to go through 10 oscillations if it's oscillating quickly. Dividing by 10 in that case to find the period. Does it match what you get with this equation? Mm-hmm. You'd have to know K, by the way.
Where does the equation come from?
That's the period of trig functions like this.
Okay,
Just
so
knowledge about those
because
trig
it
functions.
oscillates between 2 pi and...
Because a trig function has an input, well, the trig function, like cosine or sine, will go through one oscillation as the input goes from 0 to 2 pi. That means you find the period by setting this equal to 2 pi and solving for t. And you get this.
Alright, thanks.
The frequency is the reciprocal of the period. And so that would be 1 over 2 pi times square root of k over m when you simplify it. And if time is in seconds, that would be in hertz. So if the oscillations were really fast, the period would be small and the frequency would be high. If the oscillation is slow, the period is high and the frequency is small. So again, if you know m and k, you can use it to check to see how if this model is performing well. If you've got confidence that it's performing well, in another situation, you can use it to, for example, figure out k. If you didn't know what k was for a new situation with a new spring. K is called the spring constant, by the way. It doesn't depend on the mass of the spring itself. Is it a stiff spring, really thick, say, or is it a slinky at the other extreme? Okay? So, guessing can find us the answer here. How is this related to this other thing I want to introduce today? Systems of differential equations and something called a phased plane. This one second order equation, which I will rewrite up here. The second derivative of x with respect to time is negative k over m times x. That is equivalent to a system of two first order equations. This equation is second order because it involves a second derivative. When your differential equation involves a second derivative, it's called a second order equation. Second order equation. It turns out to be beneficial in many circumstances to convert such an equation to a system of two first order equations that only involve first derivatives. How? Essentially by introducing a new variable, let v be the velocity. I'm going to create the corresponding first order system. Let v equal dx dt. Zoom in on that if it's not real bright. We'll go back to black here. I haven't written the system down yet. This is just the introductory definition I need to do to get my system. Let v be the velocity, dx dt. This equation defines what v is. It also becomes one of the equations in your first order system. The other equation is found by differentiating both sides of it. dv dt is the second derivative of x with respect to t, which is negative k over m times x. These two equations together form your first order system, though they are more often written with dx dt on the left side of the first one. Dx dt equals v. And we already have dv dt on the left side of the second one. We'll just leave it that way. And as is often the case with systems of equations, we put a curly brace there to emphasize that these equations go together. The solution, your general solution of the first order equation is one scalar valued function. Output is a real number. The solution of the corresponding second order, or excuse me, corresponding first order system is a pair of functions, an ordered pair, which is really a parametric curve in the plane, in an XV plane. Let's add initial conditions in here to make things simpler. So this was the general solution of the original second order equation. I'm not proving that, but that is true. It can be used to solve any initial value problem. If I add in a couple initial conditions, like say, initial position 1, initial velocity 0, so I'm pulling the mass away from equilibrium 1 meter and letting it go from rest. Using those initial conditions, I can solve for capital A and capital B up here. Think about it here. In order for x to be 1 when t is 0, when t is 0, this goes away. Sine of 0 is 0. When t is 0 here, cosine of 0 is 1. A must be 1. It turns out if I use this condition on the derivative of this, the velocity, since the cosine becomes a negative sine, and sine of 0 is 0, and the sine becomes a cosine, and cosine of 0 is 1, it turns out b equals 0. So what I'm trying to say here is that with these initial conditions, the unique solution of the initial value problem is x equals cosine of square root of k over m times t. A is 1, and b is 0 for those initial conditions. Follow that? Do that on homework. If you want to confirm it, again, you plug in t equals 0 here. That allows you to see that a is 1. Differentiate this, which I did not bother doing. Plug in t equals 0 there and set it equal to 0. You will see that b must be 0 as well. A is 1, b is 0, so the answer is just this. Coming back to the first order system, what's the solution of the system? It's an ordered pair, 2 coordinates, x is a function of time and v is a function of time. We already know x is a function of time, right there. To find v as a function of time, just differentiate that. So if I add my initial conditions in here, the same initial conditions as over there, the unique solution of that initial value problem is an ordered pair x comma v equals cosine of square root of k over m t, comma v, the derivative of x, which will be, by the chain rule, negative square root of k over m times sine of square root of k over mt. Can you see that? Okay. Cosine of square root of k over mt is what x is as a function of time. V, the velocity, which is the derivative of x, is the derivative of that. Negative square root of k over m times sine of square root of k over m times t. This is an ordered pair. It's a point in the plane. It's a point that moves as t changes. It's a parametric curve ultimately. It traces out a parametric curve. Let's go ahead and graph that parametric curve on Mathematica. With ParametricPlot, just like we did in the past. I will go ahead and, for sake of simplicity and time, pick values for k and m. I'll pick k as 0.1 and m is 1. Let's let x of t be cosine of square root of k over m times t. Let v of t, not y of t, v is the velocity, the derivative of x. I can actually just type x prime of t, like that. And if I want to confirm v has the right formula, I can do that as well. Okay, it put k and m in there. Square root of k over m is about 0.316. I can now plot this with parametric plot. X of t comma v of t. T goes from 0 to what? The period is going to be 2 pi over that. Zero to 2 pi. Well, let's figure out what 2 pi over that is here. 2 pi over 0.316228. The period's close to 20 seconds. This is a very slow oscillating mass. I'll go ahead and put 19.8692 in here. For the plot range, let's go -1 to 1 in both directions. So we see a curve. It looks like an ellipse. And in fact, it is an ellipse. And as we always want to do with parametric curves, if we want to animate them, I can change this to a B. And to manipulate, I can let B go from just barely bigger than 0 up to that 19.8692. We'll see an animation of the parametric curve. This is not the motion of the mass. The mass does not move in an ellipse. What this is showing is the x and v values as time goes by. Initially, at time 0, you're at this point. X is 1, v is 0. I've pulled it 1 meter from starting position and let it go from rest. After a little bit of time goes by, the mass has moved to the left a little bit, so x is a little less than 1. And it's speeding up in the negative direction, so the velocity is negative. The velocity reaches a maximum negative velocity, so to speak, when x is 0, when you're passing through the equilibrium. When you come over here, the mass reaches position -1 when the velocity is 0, and then after that point, then the mass starts moving the other direction. So it's not a picture of the motion of the mass. The mass is not moving on an ellipse, it's moving back and forth. It's keeping track of the x and v values, the position and velocity for the mass as time goes by. This is a solution curve in what's called a phase plane for this system. We'll talk more about what that means on Wednesday.